Hello everyone, this is SS Patil, Assistant Professor in the Department of Physics, Yashwantrao Chavan, Institute of Science, Satara. Here we are going to learn about a very important application of perturbation theory in quantum mechanics, that is star effect. So let me start this star effect. As we know, the star effect, when a static electric field is applied to an atom, then the spectral line splits up. This effect is known as star effect. This effect was first observed by a German physicist, Johann Star, in 1913. So, as we know that in an atom there are a number of shells around the nucleus, and the energy of each shell is different. For different quantum number, the energy value is different. And when an electron makes transition from higher energy orbit to lower energy orbit, there is an emission of photons. When an electron makes transition from higher energy orbit to lower energy orbit, there is emission of photons in the form of light, and that we can observe in spectrometer. In this spectrometer, we can observe spectral lines when there is a transition from high energy orbit to low energy orbit. And hence, if we place this atom in the influence of electric field, due to the influence of electric field, the spectral line split up. This is the star effect, and we know that this electric field will interact with the atom where there is a positive charge on nucleus and negative charge on electron. So it acts as a dipole. Hence, due to this influence of electric field and the dipole moment, we observe splitting of spectral lines. Energy levels get changed. So let me understand this example in quantum mechanical basis. So we know that in perturbation theory we have perturbation Hamiltonian H is equal to H0 plus H dash, where H0 is unperturbed Hamiltonian and H dash is perturbed part, and H is the total Hamiltonian. So in case of hydrogen atom, we know that what is H0. H0 is the Hamiltonian for unperturbed system, that is our atom, and in that particular for that particular hydrogen atom, for that electron, what is kinetic energy and what is potential energy, that is important. And then we get this H0, that is unperturbed Hamiltonian, that is E square by 2m is the kinetic energy and minus E square by 4 pi epsilon 0 r is the potential energy. And here we have this H0, which is unperturbed Hamiltonian. And now when we apply the electric field, at that time, due to that electric field, perturbation is added. That electric field will interact with the dipole moment, and we have minus E r bar dot E bar is the perturbation Hamiltonian. Here E bar is the applied electric field. So now we can write like this: H dash is equal to minus E r bar E cos theta. Okay, so now we will start the actual discussion about the first order star effect for ground state of hydrogen atom. What is the meaning of ground state of hydrogen atom. Hydrogen atom have only one electron, and for that electron, ground state means that electron should be in the lowest energy level. It will be in the lowest possible energy level, and that is equal to, for n equal to 1, that is for that principal quantum number should be equal to 1. So that for one electron should be in the lowermost energy orbit, and that orbit principal quantum number will be n equal to 1. For n equal to 1, what is the value of L? L is the orbital quantum number. That orbital quantum number varies from 0 to n minus 1. So we have n equal to 1, 0, 1. So for value of L, there is a 1 value, that is 0. And hence, what is ml value? ml varies from minus L to plus L. So ml value will be also 0. Now we have 1, 0, 0. And we know that the energy for ground state of hydrogen atom, or the first shell energy of electron, is minus 13.6 electron volt. So here there is only one state having energy minus 13.6 electron volt, and that state refers as 1, 0, 0. 1, 0, 0 is the state for which energy is minus 13.6 electron volt. And here this case is known as degenerate case. Degenerate case means what? Non-degenerate case. Non-degenerate case. Non-degenerate case means there is only one state having this much amount of energy. So if there are more than 2 number of states having the same energy, at that time we can say there is degenerate state. But in case of ground state of hydrogen atom, it is non-degenerate case. And when we deal with the non-degenerate case, we have the perturbation theory. According to perturbation theory, we have the formula for correction of energy is E dash is equal to psi star H dash psi. That is in the form of integral form. Integration of psi star H dash d tau. Okay. Now to find the correction energy in case of ground state of hydrogen atom, we must know the value of psi and psi star, and that psi and psi star is for 1, 0, 0. For 1, 0, 0 case, that means n, value of n is 1, value of L is 0, and value of m is also 0. 1, 0, 0 case. So we know that there is a wave function for hydrogen atom, and we have the various states of hydrogen atom, that is ground state, first excited state, and so on. So for each state there is a different wave function. So let me have this look for the wave functions for the hydrogen atom. Here you can observe 1, 0, 0 state. You can observe 2, 0, 0 state. Here there is 2, 1, 0 state. For those states we have the different wave functions. So we can use these wave functions to solve our problem. We have the problem E dash is equal to integration of psi star H dash psi d tau. So we can use this psi for 1, 0, 0. That 1, 0, 0 is for n, L, ml. So let me use this, and if we do the calculations, if we do the integration, then definitely we have the answer that is equal to 0. We will get the value for E dash is 0 in case of ground state of hydrogen atom. Okay, that means what? There is a no energy correction when electric field is applied to hydrogen atom which is in the ground state. That means what? There is a no splitting of energy levels, no splitting of the spectral lines when a ground state atom is placed in the electric field. Okay, so now we will go to the next, that is first order Stark effect for first excited state of hydrogen atom. First excited state of hydrogen atom. So as we had seen for ground state of hydrogen atom, what is the value of n, what is the value of m, and what is the value of l? Principal quantum number, orbital angular momentum quantum number, and the ml, that is magnetic quantum number. In case of first excited state, that single electron will go to the n equal to 2. That means for n equal to 2, we have two values of L, because L varies from 0 to n minus 1. Value of n is 2. Hence, there are two values for L. Principal orbital quantum number have two values. One is L equal to 0 and L equal to 1. When we look for L equal to 0, there is a single value of ml, that is ml equal to 0, and for L equal to 1 there are three values: minus 1, 0 and plus 1. So there are total 4 different states in this particular first excited state of hydrogen atom, and each state have energy is equal to minus 3.4 electron volt. See, this is the 2 0 0 state, that is n equal to 2, m equal to 0 and l is equal to 0. Second state will be n equal to 2, l value will be 1 and m value is 0. Next 2 1 1 and 2 1 minus 1. So you can observe in the bracket 2 0 0 means what? N, L, ml, values of n, l and ml. Okay. So with this we have 4 different states having energy 3.4 electron volt. Hence, if there are more number of states observed having same energy, we can say there is degenerate case. It is a degenerate case now, and we have to handle this problem by considering degenerate case. Why it is degenerate? Because there are 4 different states having same energy, that is 4-fold degeneracy, and for this type of degenerate case we should have to apply correction energy formula as on the screen. E dash is equal to determinant of H11, H12, H13, H14, H21, H22, H23 and so on up to H44. We can solve this energy correction by using this formula. But the question is how to calculate H11, how to calculate H12, how to calculate H13. That we can see in the next slide. That is H11 will be equal to 200 H dash 200. What is H12? H12 will be 200 H dash 210. Now you can understood in this way we have to construct that determinant H11, H12, H13 and so on. And we will get that particular energy E dash, which is the correction in the energy. Okay, so now if we calculate the each and every integration for all total 16 integration, most of the answers will be equal to 0. Only there are two terms which are non-zero. Those are H12 and H21. Here only H12 and H21 will get non-zero answers, but otherwise all the values will be 0. Now it is very easy to solve this determinant. Now we can do like this. E will shift to the RHS, it becomes minus E, and that is diagonal matrix, and hence we have minus E dash 3 A naught E, and all terms 0 other than diagonal parts. Diagonal terms, diagonal elements are only minus E dash, minus E dash. So we can now calculate minus that E dash very easily. We have this E dash square into E dash square minus 3 A naught E whole square is equal to 0. Now very easily we can observe there are 4 values of E dash. That means there are 4 different energy correction values for 3.4 electron volt. There are 4 corrections. That means there are 4 different states. For each state there is a different type of correction. So now we have these 4 values of E dash. E dash is equal to 0, E dash is equal to 0, E dash is equal to plus 3 A naught E capital E, and fourth value is E dash is equal to minus 3 A naught E. So these are the 4 different values of energy correction for the first excited state of hydrogen atom. Now we can add these correction into the energy. Energy, we know that for first excited state, energy is minus 3.4 electron volt. So let me add these corrections in that. As we see in the earlier case, for ground state, there is no splitting of energy levels, no splitting of the spectral lines. But here, there are total 4 different spectral lines from a single spectral line due to the application of electric field is observed. So that we can see in this way. So now we have n equal to 1, n equal to 2, and for n equal to 1 there is no splitting, that the correction energy E dash is equal to 0, and hence that E is equal to minus 13.6 electron volt. But when we look to the n equal to 2, here n equal to 2, the energy is minus 3.4 electron volt, but energy correction is there, and we have to add that correction for the different cases. And we can observe E equal to minus 3.4 electron volt minus 3 A naught EE, and higher energy is E is equal to minus 3.4 electron volt plus 3 A naught EE. So due to the change in the energy, there is a splitting of spectral line is observed in the spectrometer. This is the story of the Stark effect, why we observe the star effect. When the electric field is applied to an atom, there is a splitting of spectral lines. With this, I hope you understood. Thank you.